All right. Hey guys. Hey everybody. Thanks for the intro, Alexi, and thanks for being here, everybody. I think this is going to be a fun discussion. Yeah, this is about, as Alexi said, distributed transactions in YugabyteDB, and it's about aspects such as scalability, performance, multi-region deployments, and so on. So there's a number of aspects. I've tried to keep a few of them, like just to give an idea of some of these aspects in this talk. But if there's any specific area of interest, please feel free to ask. We can go into that area, right? Quick intro, as Alexi said, I'm one of the co-founders and the CTO of Yugabyte. We started the database, building the database about 5 years ago, so in early 2016. And before this, I've been in R&D most of my career. So before that, I was at Nutanix for about 3 years working on distributed storage. Before that, at Facebook for 6 years, where I had the good fortune of being one of the original developers in what we open sourced, and today as Apache Cassandra and subsequently HBase. And we were also the team that ran the database as a service, right? Like we would respond to alerts and all of that. So yeah, it wasn't fun at the time, but good learnings from there. So okay, so quick intro to what YugabyteDB is, in case folks don't know, and there's just going to be a couple of slides. When we started building the company and the database, right? Like our idea was, let's think about how we design the perfect distributed SQL database for users building cloud native applications, right? So the simple story is, on the left, you have Postgres as one of the fastest growing databases. And on the right, you have Google Spanner, which is an RDBMS that's built for the cloud. The thing is, Postgres has a great feature set, but is not cloud native. Spanner is cloud native, but doesn't have the feature set of Postgres. So our simple idea was to take the two sides and marry them together, right? Like take the Postgres upper half as it is, right? And so our first attempt at doing this was to actually try and rebuild Postgres in a cloud native fashion. And then we realized it's just no mean feat trying to do 30 years of development quickly, and it's going to take a very long time. So we said, you know what, let's go the other way of reusing Postgres, which had its own risk, right? You have to somehow get a complex code base to work with another complex code base, which is distributed systems and transactions and so on. But now we're past that stage, and so yeah, this is a little bit of all of this is also about how things work in Postgres. So happy to talk about that side as well. Again, to just quickly contrast the two sides, YugabyteDB is 100% open source, so you folks can look at the code, download, and try it for yourself. It's fully Postgres compatible because it literally reuses the upper half of Postgres. We care a lot about the enterprise-grade nature of the database as well, so backward compatibility, rolling upgrades, security, et cetera, et cetera. You can deploy it public, private, hybrid, any of these clouds, and high performance is a core tenet of the database. Hence, we started writing this in C++, right? On the comparison side, if you look at it, the idea is simple. Retain the stuff in Postgres that makes it really popular. So all of the RDBMS features in the SQL ecosystem, because it's literally Postgres your app still is talking to, and bring in the very good features from Google Spanner. So high availability, horizontal scale, and distributed transactions, right? This talk is, of course, about the distributed transactions aspect of it. And finally, the data replication, we didn't want to compromise on async replication, which is very critical to the RDBMS world. So with Yugabyte, you can do synchronous replication within a cluster and asynchronous replication across clusters, right? So you can do those type of deployments. At a high level, 10,000-foot level, it's never this easy, but anyways, you can kind of logically separate Postgres SQL into two layers. You cannot actually easily separate it from the code level, but this is just like a diagram, so we can do whatever we want. So the upper half is the parser, analyzer, rewriter, planner, and executor. So everything related to the language layer or the query layer of Postgres. And the lower half, let's call it the storage layer stuff, which is all the background writer, wall flusher, vacuum, all of that stuff, right? The lower half that deals with the disk. With Yugabyte, our first step was to actually make the query layer stateless and capable of talking to a distributed substrate, and replace the storage layer with DocDB, which is Yugabyte's distributed storage layer underneath, right? So this is just like the way we reuse the Postgres query layer, right? Then some of the things that we needed to do, I mean, if you just look at the diagram as it is, what this means is every query layer is capable of handling a query from the client. However, it has to read all the data to that query coordinator, right? Which can actually be bad. So the next step is to actually figure out how you start pushing down different pieces of work down to the nodes to act closer to the data. But it's also important when you have transactions to do this work in such a way that all of the independent pieces of work actually happen at the same atomic time or as a unit, right? So that's also equally important. So this talk is more focused on how we do transactions firstly, and how we get a little bit of performance out of transactions, right? Because once you start going into a distributed world, the way transactions work can be radically different from the way they work in a regular RDBMS. Okay, so the first thing to cover is, let's take the simplest possible case where you insert a row, right? Like, and just lay the background foundation for how you would insert a row into this distributed substrate. And we call this the fast path because you don't have to do any coordination across nodes, right? So, and as the name suggests, we would really like to do this all the time if possible, except it's not so. So let's talk about this single row transaction, right? So the basics, right? Like, firstly, we want to distribute data across zones, regions, clouds, whatever it is. So let's assume that you have 3 nodes across, 3 fault domains, whatever they are, and you now have to distribute data across these 3, right? So the first thing is you have a logical user table, which has a bunch of rows. The table is transparently and automatically sharded by the database, so the user is not aware of this. Into tablets, or the user can influence how the table gets sharded, but it's done transparent to the user, right? So each tablet, or a shard is called a tablet, is actually a group of rows, right? So we don't break a row halfway. An entire row is stored inside every tablet, right? And this type of sharding, like I said, is transparent. This example shows a table being split into 6 shards, right? That's just so that we can display it better. We don't have to draw too many of these, but in reality, you could have like a lot of shards. Like we typically like try to, the reason to have shards is also to help distribute data for query processing, but also on a failure, you want to redistribute the queries to many nodes, not just to one other node, right? So having many shards per node is actually useful, right? So in practice, we would have 8 to 10 shards per node, right? Like as of data. Okay. So the next piece is, now you take 1 tablet's worth of data. That's really the unit at which we're going to synchronize replication of data. And replication is needed, obviously, for fault tolerance. So we want to make sure that the failure of a node actually means, if you want to survive that, you really have to have the data replicated. So take this tablet's worth of data, which is really an exact set of rows. And there's this, again, 2 properties of the tablet, if you recall from the previous slide, which is every row belongs to exactly 1 tablet. And all the tablets together comprise the entire table, right? Like, you cannot have holes. You can't have some data not assigned to something. So it's very tight in the way it's done. So now you take 1 tablet's worth of data, and we use the Raft algorithm for replicating this data across nodes, right? So if you folks remember what Raft gives you, what Raft does is effectively you will have 3 peers called tablet peers at the start, where you designate, hey, 3 of the nodes host the data for the tablet, and they become tablet peers, and they start a leader election. 1 of the tablets win the leader election, right? They all propose, and you guys know the leader election algorithm. Once you have the leader election, and once a leader is elected, the leader has to keep renewing his lease, so to speak, and everybody else is watching and waiting for the leader to fail to keep that quorum alive. And all the user queries, whether it's a read or a write, that are consistent and have to work as a database, actually are handled by the leader, right? So this ensures, and what Raft ensures is a few interesting properties that are useful. Firstly, any update that goes to the leader can be linearizable, right? Like, as in the exact set of updates in the order in which they are processed or received can be ensured, like they get queued into the Raft queue, and the timestamp that you get back for the user, they can guarantee that there's no change irrespective of failures or a variety of different things. The couple other interesting things that Raft allows for is, in addition to tolerating failures, is also dynamic membership changes, which are actually really useful in practice. Like, for example, if you're trying to add a new node, the way this happens internally is you take 1 tablet at a time from the table, and you increase its replication factor temporarily from 3 to 4, and then drop an existing node. So you can kind of move your tablets over to a new node or a new set of nodes using the Raft algorithms, dynamic membership change. The second use of dynamic membership change is actually to replace a machine to in-place upgrade to a larger set of machines. Like I am on 4 core machines and I find that my 4 core machines aren't working well, or maybe the cloud provider has a newer generation of machines, so I can actually replace my old machines with new ones, right? So these type of things Raft enables, right? So anyways, every tablet is replicating data using Raft. Now, this is how our 6-tablet table example starts to look in a geographically distributed setup. Okay, so assume that the same table is replicated 3 ways across 3 different zones or regions, right? So in this example, you find that the same colored disks, which represent tablets, occur in each of the fault domains because you want to have 1 copy of data per fault domain. And the other diagrammatic representation is that the cylinders with bold borders are like solid borders are the tablet leaders, and the ones with the dotted borders are the followers, right? So this shows a couple of these tablet leaders, each running their own Raft group, right? So each of them form their own Raft group. And if you have a failure, then you re-elect a leader in a matter of seconds, right? Like, so because the way for a multi-zone deployment in a public cloud, what we've found is we set typically the tuning parameters of number of missed heartbeats to detect a failure at 6, and the interval of heartbeats to about half a second, so 500 milliseconds. So it's about 3 seconds to fail over, right? That's typically what we see as the disruption on a node failure. So when a node fails, many other nodes take its spot, and they do so in about 3 seconds. So if you tune your queries right, as in if your queries are able to tolerate some level of higher latency on a failure, then you can tune your queries to be more than 3 seconds in their total timeout, in which case you won't see timeouts, you'll see high latency. Or the other side is you'll see some timeouts and you can retry on the app layer, right? It really gives you the control at being so. Okay, the couple of other details here. The first thing to note is that this is just a 3-node example, but imagine that the tablet leaders are balanced across nodes, and the tablet followers are also balanced across nodes, right? So this gives you the property that every node has 1/3 of the total tablets it hosts as leaders and 2/3 as followers if the replication factor is 3. So and similarly 1 by n, and n minus 1 by n if it is replication factor n in general, right? So the leaders are the ones that actively take reads and writes. The followers are mostly doing replication and waiting to take over. And this ensures that the load that comes to any one table is evenly distributed across all nodes. So that's point number 1, right? Point number 2 to note here is that we have control at moving all the leaders to one region or zone or the other, right? Like we can actually configure dynamic policies to say, hey, move all of these tablet leaders to just zone A or region A, right? And you can start serving and coordinating stuff from the first region. Okay, so a couple of, like the third point to note is that this rebalancing is done at a per table level, right? Like, so it's not just tablets, because you could have tables which have a lot of reads, a lot of writes. So you want to redo this balancing at a per table level to make sure that you distribute or maximize the policies, or at least follow the user policies per table, right? So these are some of the interesting things to note. Okay, so far we don't need any time synchronization, and the reason is because you can just get away with time deltas and deadlines as opposed to deadlines, right? You don't need the actual time, like you don't need to use the UTC or the wall clock time so far. You can just get away with time deltas, right? You can say, hey, your lease is valid for another 1 second, and instead of using clock skew, you could use clock drift, right? So Yugabyte actually does that. Like, in fact, the Raft algorithm as proposed without any of the, there's a small paragraph which says you can make it better by doing this, but without that paragraph actually forces you to do a quorum read on every read internally, right? So every read that comes into the tablet leader, it has to replicate to the quorum to make sure it's still the leader, right? This actually kills performance if you are specifically going for geo-distributed workloads, because nobody wants a database that's both slow on reads and writes. If geo-distributed, they might as well not use it. So we said like leader leases are extremely critical, and leader leases allows a leader to serve data without having to consult or re-replicate reestablish its leadership over the Raft group, right? So we use leader leases. That means the leader can serve, but if you want the leader to serve, you have to know like nobody else can become the leader while the leader has the lease, right, for the interval of time for which it is serving. So the way we ensure that is the leader actually uses Raft itself to replicate a time interval for which it's the leader, which is renewed with every heartbeat. So every 500 milliseconds, it renews a 2-second leader lease, right? So again, the timings are 3 seconds to detection of failure, 2-second lease period, and every 500 millisecond heartbeat. And the 2-second is a rolling renewal of the lease every 500 millis, right? So it's a sliding window where the leader keeps saying, I am the leader for the next 2 seconds, every half a second to its followers using Raft itself, right? So it's kind of using the same mechanism. So now that we've solved the clock skew problem, you don't need time synchronization. The next piece is we don't use wall clock, we use the hardware tick, which is called clock monotonic. So it's the hardware time on the machine. And that really makes sure that you've eliminated any NTP-based adjustments or clock jumps or all of the other crazy things that can happen with time, right? So I think the combination's working pretty well. I think this is from the Jepson report where, Kyle tried to break the database and tried really hard to break the database, actually, and he does a fantastic job. But he doesn't go theoretical. He tries to practically prove that he's able to break the database, right? So what he noticed was that with the system that he had back then, it was really hard, and I think he ended up redesigning the way his whole framework works to make sure that he's able to catch things like these. But anyways, the good news is that, for practical systems, it's actually, even in the cloud, it's actually quite robust to, these type of, like, people are worried about VM live migrations or this or that, right? So these are things we ask people to disable typically if they want to be safe. But in realistic heuristic terms, it's pretty safe, right? Okay, going over to the next section. Hopefully I didn't go at, I went at the right level. Hopefully everybody's able to follow what I said so far with respect to leader leases and, Raft and so on. And let me know if, this is, I need to go at a different level or a different speed. So the next step is, we talked so far, if you recall, only about the fast path or the single row or single shard transactions, right? So now, before going into distributed transactions, the first thing to realize is that you need time synchronization for them, right? Because now you're dealing with different Raft groups, not just the same Raft group, right? And why is that? So this is how it starts to look, right? So you do a begin transaction, and then you do update row 1, update row 2, and commit, right? And the fact is, row 1 belongs to one Raft group, which is on one set of nodes, and row 2 is on another set of nodes belonging to another Raft group. And both these entries have to commit and be visible to the user at the same time. So that's really the statement of the problem, right? So, and the key there is that the nodes need to agree on both the time at which the update was made and the time from which the update is made visible to the end user. Both, they're two different values, right? They could be two different values. So in such a way that, no other update comes before, you guys know what the transactional nature of a database is. If you have committed a transaction at a time and you made a read of that transaction, you can in future no longer have another transaction go at an older timestamp, right? That's going to violate the ACID semantics or the transactional isolation guarantees. So how do we do time synchronization for this, right? We'll focus on that first, and then we'll go to the actual distributed transactions algorithm, right? So we use a hybrid logical clock, which I think Alexi definitely is super familiar with, having done some of the original research on. But anyways, the idea is to combine a coarsely synchronized physical clock with Lamport clock, so if you just look at the two sides, right? A physical clock by itself doesn't cut it, because your best bet at getting it synchronized is NTP, and you're going to have 100 to 250 millisecond skew between nodes, right? And nobody wants to. And what Google Spanner does is it has physical clocks, is the atomic clock true time service, which is about 7 milliseconds in skew. Now, if I tell you, hey, here's a database whose minimum latency is 7 milliseconds, you're saying, okay, that's not too bad. 7 milliseconds I can live with, right? But if I come back and tell you, hey, how about a database which has 250 milliseconds? You're like, dude, are you kidding me? Why do I even need a database, right? So that's really not going to work. And if you look at only Lamport clocks, right, that's going to force a different kind of a trade-off where there is no notion of time across different Raft groups, because everybody uses a Lamport clock. What is physical time when you do, let's say you're doing 5 different transactions in parallel, and the 6th transaction comes in, which just wants to select from the table across these 5 tablets, right? what is the meaning of time across these tablets if you don't have something to give you the causal relationship between these 5 tablets? Like, you don't have any, right? So if each of the tablets kept generating like a logical ID, the IDs could be at very different numbers and mean nothing in terms of causality, right? So if you're purely going with a logical clock or a Lamport clock, the way to do this is to have a central system issue time, so that the logical clock value issued by one Raft group actually has a relationship to the logical value by another, right? Now, that was not okay for us because we wanted a geographically distributed deployment, and you could get into a scenario where you have 3 different regions and your timestamp oracle, or the central authority that issues this timestamp, is in one region, and your transactions are happening in another region, completely self-contained, but they can't make progress because you're partitioned away from the region that has the timestamp oracle, right? So these type of deployments kind of kill geographically distributed topologies, and our thought is, like, having seen many services and databases at Facebook, like the public cloud and cloud native applications are going to evolve to where multi-region, multi-zone, and cloud deployments are going to be norm, right? Like, and all kinds of replication and stuff going on between them. So if we assume that as a fundamental, then the next reasoning we did was that time synchronization services will improve, and so we went for the logical clock. Anyways, so what is the logical clock, right? The logical clock uses a 2-part clock. It uses the physical component to track time in a coarse manner, and uses a logical component to track operations and causality within that coarse window in a more fine-grained manner, right? So it gives you the best of both worlds, because in the worst case for safety, you can always fall back to the larger latency. But in majority cases, like more heuristically, you will be relying on the logical components and how they normalize time using communication between the nodes, right? So we rely on the frequent communication between nodes to normalize time, but rely on the max skew between nodes in order to detect safety and be safe, right? And this clock is exchanged on every heartbeat, right? Like, so every single heartbeat would exchange your hybrid logical clock time, and 2 nodes would compare their clock, and the node with the bigger clock would impose that physical time on the node with the smaller clock. So everybody's physical component keeps going up with this hybrid logical clock service, and the node which has the fastest node in terms of time, right? The node with the largest physical time keeps pushing its time to all other nodes, right? So I'm just assuming folks kind of know what HLCs are, and I'm not going into too much detail, but if there's questions, happy to do that. Okay, so specifically how HLCs are encoded in Yugabyte, it's a 64-bit value, 52 bits for the physical time, which gives you microsecond precision, and 4096 to 12-bit value for the logical component, which is 4096 values most, right? So, and we felt that this type of a split is good enough for most of the operations we do. And I mean, there are more tricks in the database underneath the hood, like, for example, we do what are called group commits. It's worth mentioning in this context, where if there are a number of operations that are outstanding inside a Raft group, we don't take each one of them and then replicate them one by one. We can send them as a group, right? And we'll be able to, like, what is the size of the group and how we issue hybrid logical clock values for all of those updates inside the group can be, like, a relatively coarse. Like, we could have multiple operations going into the same timestamp if needed, specifically if they're a part of the same transaction and so on. So that 4096 value is typically not a problem in practice, right, for an OLTP system. All right, so let's look quickly at how this works, like, and the way, like, hybrid logical clocks actually provide an interesting trade-off with respect to performance as well, where you don't necessarily always have to introduce a commit wait, because specifically in smaller clusters, you don't come across islands that much. All nodes are forced to communicate with most other nodes for something or the other, right? And plus, we have this 500 millisecond heartbeat system that normalizes time. So there's enough communication going on where the cluster's time keeps getting normalized very quickly. But roughly, this is how it works. So let's take 3 nodes, and we're going to start the observer's clock at T0. Like, there's a lot of notion of time here. So our notion of time as observers is T0. Node A has a wall clock running at 1200 and its HLC is something, right? Node B is at 1000 and node C is at 1100. So if you kind of compute the skew as an observer from node A, node B skew is 200 milliseconds, is 200 milliseconds behind, and node C is 100 milliseconds behind, right? So if you get some update request, you start, you have to process it and then start replicating, right? And then the minute you start replicating, let's say the hybrid timestamp assigned by node A was, 1201 comma something, right? Some logical value. And you start replicating to A and C, right? Now, obviously with the time has now progressed by a second or a millisecond, whatever that value is, 1 unit of time, right? Now, let's do something, right? Let's say that node A, B, C are in different geographies, and it takes twice the amount of time for the replica to C than it takes for B, which means B is much closer to A than C, right? C is twice as far away. So let's say that's the case, right? Now, time has moved forward by 1 second for us, or 1 unit for us, and 1 unit for each of the nodes, right? The skew, however, remains the same, because we're kind of assuming that the clock drift is easier to bound than the clock skew, right? Like it's, and which is typically true. Okay, so the next transition is after 1 more unit of time passes, node B actually receives the message, right? And what you see is that it receives the message and the update at 1201 is the physical time. Its own physical time is 1002, 200 milliseconds behind. And what it says is it starts comparing these two values, and it says, look, I have received a message. It can be any message, right? An update, a heartbeat, whatever it is. I've received a message from node A, and its physical time is 1201, and my own is 1002. My notion of physical time is lower, so I need to upgrade. And so it's going to upgrade its physical time to 1201. And it's going to stay there until it gets either a different message or its own clock catches up and goes past, right? So, and so its skew, the minute that update happens, drops from 200 milliseconds to a millisecond, right? Like, which is really, really small at this time. And if you look at C, it's still in flight. It's still 100 milliseconds away, right? Like in terms of clock skew. Now, let's say the next image, you have 1 more unit of time progression. And finally C receives that message, and now it's going to update to 1201, and because its own time is 1103, right? So it's going to update this time, while node B, even though its time moves forward, its wall clock time moves forward by 1 unit, it will not update its HLC, right? So and so its skew increases to 2 milliseconds, whereas the skew of node C drops to 2 milliseconds from 100. So this is a very quick scheme where the normalization happened very quickly. The advantage of the scheme is that in many cases, you don't need to introduce commit wait, right? But of course, what you give up is, so there's a trade-off even here, right? Like you get this performance, but what you give up is what is called external consistency or linearizability when you're dealing with distributed transactions, right? So that means if you're doing 2 transactions on 2 different nodes using the HLC scheme, and let's say you start transaction 1 first, and then you start transaction 2. With the HLC scheme, you could have transaction 2 commit first and transaction 1 after, right? You could have an inversion in the order. But note that these are not acknowledged to the user. So this is still serializable, because serializable transactions, they are defined as a concurrent execution of transactions that pertains to some serializable order, right? So that means if I do T1 and T2 at the same time, it can be T1 comma T2 or T2 comma T1, either one, right? However, an external consistent system or linearizable system says, if you do T1 and then I start T2 from a client, T1 will finish before T2, right? So with atomic clocks and a 7-second skew, Google Spanner actually is linearizable across nodes. But we think that in distributed systems, you're practically okay with a distributed database. The value you get is so much higher that you can give up this property and still survive in SQL terms, because we believe not too many people exploit the linearizable property across nodes or of independent transactions. They usually encode the logic inside transactions and make the transactions dependent on each other. So we give up that property, but what we get back in return is you don't have this fixed commit wait 7 millisecond skew, right? So you can actually go much faster. Okay, so there is a pathological case with using hybrid logical clocks, which is that like as we said, most of the time, for all heuristic practical purposes, the RPCs between nodes are so often and frequent that it forces quick time synchronization, and you anyway have the heartbeats and a bunch of stuff. But sometimes that could not be the case, right? Like, for example, I update in Raft group 1 and update in Raft group 2, and before my 500 milliseconds have expired, I come in and do a select star across these two Raft groups, and there's really no exchanges between these Raft groups in the pathological case, right? So in these cases, the database transparently detects conflicting transactions and tries to retry if possible, otherwise throws a user-facing conflict, right? So it is almost, you could say, science that you should expect more conflicts, but the trick is in reducing the number of conflicts, right? Which is why performance actually is in the database's own favor. It's not just for the user. It will reduce the amount of conflicts, the quicker you can get through every transaction. So the faster you do things, the less you have chance of conflicting. Everybody's happy, right? So both from the perspective of no conflict, but also from the perspective of, oh, this database is really fast. So, all right. So I'm going to go on to the next topic. I don't know if I should pause and see if folks have questions, or maybe let me just finish and then we can come back, right? So the next step is integrating Raft with hybrid logical clocks. So we talked about single row with Raft and multi-row with hybrid logical clocks. So this is the way they both act simultaneously in YugabyteDB cluster. On the left, Raft works at a per tablet level, but like a hybrid logical clock at a per node level. Yeah, this one should say HLC, sorry. On the left, Raft issues a Raft sequence ID. It's a logical sequence number. It has no correlation between different Raft groups. However, hybrid logical timestamps can be compared across nodes. And one is used for single row, one is sufficient for single row, the other is necessary for distributed transactions. And what the key part is the fact that they're both monotonically increasing, which allows us to correlate the two, right? So the way Yugabyte does this is, if you look at a Raft log for tablet 1 and tablet 2, I mean, there are some transactions 1, 5, 7, 2, 7, 8, whatever, right? This is the user performed transactions and their partial views as seen on nodes. What you see is that the Raft IDs are per tablet. So this is, if you look at the Raft ID, it's 100, 101, 102. However, the hybrid logical times are flowing across the cluster and they're, keep getting synchronized every now and then, right? So when a transaction is committed, effectively it'll have the same hybrid logical clock, but that gets associated to the Raft log sequence number, right? Like LSN. So we kind of use this trick to correlate stuff at the Raft level. However, when data starts flowing into the data files of the database, this is just the write-ahead log. So the data files of the database, we strip out the Raft ID and mostly focus on the hybrid logical clock value, because that helps you with scans and coming in at a particular timestamp and understanding which values to include and not, and all your MVCC is off of the HLC value. Okay, so let's go into multi-row transactions with all of that background, right? So like, it's a fully decentralized architecture. That means any node can handle a transaction, and you have a distributed transaction status tablet, and every transaction is born in the pending state and can go to either committed or aborted, right? And reads are only served for committed transactions, which means as a different transaction, isolation level guarantees that you cannot read a pending transaction. You have to go through some conflict resolution rules. You can ignore it. Some states allow that, but yeah. The isolation levels that YugabyteDB supports are serializable and snapshot. Postgres is serializable maps to YugabyteDB serializable isolation levels. Snapshot, like everything below serializable maps to snapshot, like repeatable read committed, read uncommitted, because as a transactional database, we didn't really want to support read committed and uncommitted. That's more in OLAP-ish workloads, right? Not so much for OLTP workloads. Okay, so here's how it works, right? So let's say you have a cluster where you're updating a couple of different keys or rows or whatever it is, right? So you'll get a client's request which says set key 1 to value 1, key 2 to value 2, and we're going to assume key 1, key 2 are belonging to 2 different Raft groups, right? It hits some node, it's called a tablet server, but it's just any node, right? And that becomes automatically the transaction manager. It then creates a status record, right? So it now says, I'm now performing a transaction and I'm going to do some stuff for it, and here's the transaction ID. then it starts writing provisional records for each of the updates, right? So these are not visible. These are actually written with the transaction, and the timestamp is meaningless at this point, right? So you're just writing these provisional records without knowing what the timestamp is. Note that every one of these entries are replicated using single row Raft, right? Like, so it's highly available, right? Now, once you write provisional records, you may encounter a previously existing provisional record, in which case you run conflict resolution rules. You may not, in which case you complete this whole thing and finish, right? And if somebody else comes to read this and you find a provisional record, it means you need to go to the status table to check what's going on. If that transaction is aborted, ignore the provisional record. If it's committed, fetch the timestamp and use that entry as if it were committed at that timestamp. And if it's pending, then you got to go figure out, hey, what isolation level is this? What are they trying to do? What am I trying to do? Should one of us abort? All of that stuff. So it's a conflict, right? So that's roughly how it works. So finally, then we commit the transaction after we are successful in acquiring all of the provisional records. If we're not, we have two choices. We can restart the transaction, or we have to throw a user-facing error, depending on have we returned anything to the user or not, right? So if the transaction has returned nothing to the user, we can transparently restart it and try again or do other things, right? But after the commit, two things happen. The first thing is we act the client because the system is now self-sufficient. But note that every read is now going to chase the transaction status table to figure out is it committed. So we actually flush this asynchronously to say, why don't we finalize the timestamp and remove the provisional record bit to say this is a finalized entry at this time, and now that tablet is self-sufficient. So this is how the distributed transaction path works, and I think kind of explains why we call the other path the fast path, because it's just a simple go to the tablet, make the update, 3 replicas, done, right? So, but this is necessary, right? Like there's no real easier way to do this. So just a couple of other bits as my last section, and I'll open it up for questions about achieving performance, right, in this type of a system. As we said, performance is both good for the user, but good for the database itself, because it reduces probability of conflicts, especially if it's distributed, right? So the first thing to note is we try to opt for the fast path as much as possible, right? So, and this is done transparently, so the user doesn't care about or know if what's happening under the hood. But if you do an insert into table values and you put one value in there, right? Like you put one row in there, Postgres would do the following. It would say, okay, internal transaction, I'm going to ID lock row equals 1 if you're inserting an ID equals 1. And then it's going to select 1 from the table. And then make sure that if the row is present, it's going to raise a violation. If the row is not present, it's going to insert the row and then unlock and say, I'm done, right? If we did all of that from the transaction coordinator, that would be 1, 2, 3, about 4 RPC calls, right? So, and each RPC call is 4 milliseconds, so about order of a millisecond. So you're at least talking 4 milliseconds per insert, and too many RPCs and a lot of CPU. So this cluster won't be able to scale. So the Yugabyte execution plan is as follows. You do this insert, and it's going to verify if you can use the fast path, because there are some times where the table could have a foreign key constraint, it could have a variety of triggers, it could have a bunch of stuff, right? So there is, even if it's a simple insert, you got to do some checking to make sure it's possible. And then we send that whole insert down to the storage layer, and the storage layer actually does an atomic concurrent set, like at the tablet leader, right? So the tablet leader that owns the row will actually do all of this stuff and say, I have computed that this row can actually be inserted successfully, then queue it into the Raft level, which then replicates stuff, right? So we don't repeat the constraint check and all of that on every node, and we don't use RPCs in order to insert. You push it down to the owner of the tablet leader, which does all of this stuff and then replicates. So that's one. I'm just giving flavors here, right? I'm not going very detailed into anything. There's a lot of tricks under the hood here, so that we could spend the whole hour here. So. The second one is, if you remember this diagram from before, we said step 1 was the user issues something. Step 2 was to create this transaction status record on a different node and then replicate it, right? We can actually eliminate this RPC2 along with the Raft replica round trip here by just pre-creating the transaction status record and picking an existing ID, right? So every node pre-creates a bunch of transaction IDs and keeps it ready. And so if a transaction hits a node, it simply picks a pre-created and pre-replicated transaction ID to move forward, and that just eliminates a whole chain of extra work that needs to be done. Obviously, it has to replenish itself, but you can do that in a more batched fashion in the database more efficiently. So. Yeah, the third thing is, hey, it's all about network, right? Like at the end of the day, disk is microsecond or below, and network is millisecond. So that's where the line is, right? So, so let's say you're inserting an array of values. You're inserting like a bunch of different rows. Your Postgres plan would be, hey, let's just like insert row by row and then commit the transaction. It's simple, right? But if you do that with Yugabyte, you're going to say, you're going to make one RPC call for every entry here. And if you have 100 rows, you're going to be doing 100 different RPC calls and then finalizing the transaction, which is going to be very slow. So what we end up doing is we regroup the array of insert values into per tablet batches and then flush the tablet batches in parallel, right? So it goes to multiple different tablet groups, each one of which processes the set of values, the batch of values. And if all of the batch of values actually succeed to get their provisional rights are on the tablet leader for that tablet batch, then it starts doing the Raft replicate, right? So this actually improves the performance of the system, another order of magnitude for batched inserts, right? And yeah, the other, of course, standard trick in the book is rewrite the execution plan in order to push down your expressions closer to data. Like simple thing, you want to add, the salary of all, like you want to just do sum of salary from employees. Let's just give me the sum, right? It's not really an OLTP query. You can put a where clause in there, but effectively your point is the same, right? Like some sort of expression that you're computing. You can push what Postgres would do is it just fetch all of the salary columns from all rows and then apply the sum, right? Simple. But with Yugabyte, each of these fetches could become remote RPCs. And so you're going to be fetching a lot and then adding it up in one node. Instead, we kind of changed the query to fetch sum of salaries from all of the tablets and then add the partial sums to get the full sum. So a lot of stuff under the hood, like as you can see, even though we are just talking about Raft and distributed transactions, it's not completely devoid of what the layer above does. And each one of this are like various types of primitives that we need to expose at the Raft leader level, right? And the way we do this is by reusing the Postgres libraries. Because it's C++, we can just reuse those libraries to perform a whole bunch of this stuff. Right, so yeah, as I said, a lot more like, you can eliminate sorts by laying out data the right way. You can push down limits and offsets to pull in data, just the right amount of data as opposed to a lot. You can parallelize a lot of execution inside a transaction, like foreign key checks versus insert. You can go in parallel as opposed to serializing. You can cache stuff, like if you're inserting 100 different rows, and all of those rows are referring to the same foreign key, you don't have to perform 100 different foreign key checks, right? You can cache that for the context of the transaction. So a whole bunch of things like that internally actually happen under the hood in order to improve performance, right? So yeah, I'll stop here. I think if you guys, we're happy to take questions here, but if this is interesting, folks, please feel free to join us on Slack. We always have, any type of question, distributed systems, SQL, whatever it is, it's fair game. It's a community Slack. We have thousands of folks asking interesting questions, interesting discussions. And we're also an open source project. So, if you're interested in, checking it out, doing some, features, or even playing with it, we're happy to work with you folks. So that's all I had. Maybe we'll open it up for questions.
All right. Yeah. Thanks a lot, Karthik. That was really interesting. I do have quite a few questions, but let's see if any other people have questions first. And we can record the questions, Q&A. I think it's really good.
Yeah, no, I'm happy. Yeah, I think we should. Nothing, yeah, it's fine. If you guys don't like something, I'm happy to hear that too. Hey, why do you do this instead of that? I'm happy to hear that.
So yeah, if you have questions, just speak up. I think Mahib raised a hand. You can feel free to speak up.
Hello, everyone. Mahib. Thank you for your nice presentation. Actually, it's very interesting. Well, you mentioned that one of the trade-off that the time synchronization actually give up is external consistency. Am I right? But
yes.
I'm actually interested in the time that it takes for the replicas to eventually converge. Does the client see the waits while the replicas converge, or the time is actually very minimal? It's not actually recognizable.
Okay, so So external consistency may not have anything to do with the replicas converging, because the replicas converging is a per row operation almost. The client, so I'll answer that one of two ways, right? Like the time taken for replicas to converge, right, is really using the Raft algorithm. You get an update, you replicate it to a majority, you wait for a majority, and once you've replicated it to a majority, you're pretty much good to go forward. So it takes one RPC call or a set of parallel RPCs to go to a majority, including the node itself to write, right? So assuming that the dominant piece of work here is actually the RPC call and not really writing it to your own disk, that really dominates, and that's in the order of a millisecond, right? Compare that with a traditional RDBMS like Postgres, where the write is to local disk alone, and that can be in the order of microseconds. So yes, the latency as seen by the client will go up from a micros to milliseconds. However, the client itself is going to transmit over the network in order to get to the database. So you're talking about 1 millisecond plus a few microseconds go to 2 milliseconds plus a few microseconds. So it really doesn't matter for practical systems, but theoretically, yes, the latency will increase in a distributed system. The client doesn't care about replica convergence. That's automatically ensured by the database.
Oh, that's good. Thanks.
Sure.
Okay, Liz, I think you have the hand raised.
Yes, so that was a very interesting talk. So you're really comparing with Spanner. So I was just wondering, I mean, I actually had two questions. One was, how was your performance compared to Spanner? And the second one was also that, I mean, because I didn't get that part really well. You said that Yugabyte enforces, I mean, you get linearizability, but you don't get strict linearizability, right? Like Spanner, because they are using the real clock time. So I just had those two questions.
Yes, no, great question. So let me answer the second one first. It's simpler. Yugabyte guarantees strict linearizability for single row transactions, right? So single row operations using Raft are strictly linearizable because we don't use time at all, right? Like it's effectively using Raft log sequence numbers from Raft, right? To ensure that. Distributed transactions or multi-row transactions in YugabyteDB are not linearizable. They're only serializable. That's the highest isolation level we support. Distributed transactions in Spanner are linearizable, right? Like that's going to be the difference. So they're higher than serializable in terms. So that's the trade-off that we made. In terms of performance, I think here, this would be the way I would characterize it. For a majority of workloads where I would say you don't really have too many pathological conflicts or any of those type of scenarios, Yugabyte will actually outperform Spanner in terms of latency because there is no forced commit wait, right? So there's no 7 or 10 millisecond wait for most of these things because we're not shooting for linearizable. So we're shooting only for serializable, right? That means you don't need to wait for the time on all the other nodes to catch up. You can simply exchange RPCs to normalize time, which you would have done in order to commit the transaction and just respond to the user. Spanner, however, wants to be linearizable, which means it needs all the times for all the other nodes to catch up, which means it's got to have a forced 7+ millisecond wait time, which I think practically they mention is around 11 milliseconds. So what you'll see in Spanner is 11 milliseconds on average, and on Yugabyte, it can be a millisecond or very low in terms of latency. In terms of conflicts, you'll find that Yugabyte can shoot up in the tail latency to 100 milliseconds or whatever your NTP synchronization is, and that would still be low in Spanner, right? And note that the kind of conflicts I'm talking about are app-induced conflicts. There are some real conflicts in the app where nobody can do anything about it. It's going to conflict anyway, because if you try to do 2 updates at the same time to the same row in 2 different transactions, one of them has to conflict. You don't have a choice. So I'm removing those and talking about the percentage of conflicts that you will observe in Yugabyte that will result as high latency. So it's really a small fraction of the workload in of a typical workload that would do that, right? So.
Thank you.
Sure.
Okay, anyone else? Any more questions from the audience? So I do have a few questions and a few comments for that matter.
Sure.
I really like how a lot of the basic scheme, right? So you have the basic scheme of how this transactions work, and then you do follow with like a bunch of slides and, oh, by the way, we try to do this, we try to optimize it in this and that, like in all these different ways. And all of these optimizations, they seem to try to push stuff closer to the storage, right? So that's more of an observation. I think it's like really important to understand in distributed systems, especially in the ones that can go like a geographical scale, right? It's super important to have that kind of optimizations in place. So that was really interesting to see. Totally like different perspective from a single node database like Postgres or MySQL.
Yeah, the other thing I didn't mention, it is actually I wanted to, but we would have run over time, is also the fact that you can move all the tablet leaders to a single geography. So all of your multi-tablet group or multi-Raft group operations can actually happen inside a single geography in terms of the, like you want to do a foreign key check, you want to do this insert, you want to do another write. All of those happen in the context of a single geography, and you only incur the network latency of replicating it out like a fewer number of times, as opposed to checking from a remote geography and coming back. And you go to a remote geography and you do an update, and that comes back to you because it's replicating. So you'll get into a more of a confused replication scheme. So that's the other one. It's all related to network though. So.
Yeah. On a related side, so what if I have a transaction that spans multiple tables, right? So I'm doing something more complicated that involves some relations and so on, right? Can I somehow influence the replication of these different tables or tablets so that they're closer together, so I can run these transactions faster?
Yeah, you can. And that's what I meant by the tablet leader. So effectively, if you're doing a multi-table, I mean, it's just tablets at the bottom. The lower half of the database only views tablets. It doesn't care about, tables are more of a next order grouping of tablets, right? So if you're doing something between tablets, and let's say there's table A that sits in, that's whose leader, or a particular tablet whose leader is in, say, Europe, right? And there's another table whose leader is in the US, right? And you try to do a transaction across these, right? Your transaction has to live somewhere. Let's say it lives in the US, right? For just sort of picking one of the two. Then you do one row update to the US, which replicates it to the US location and to the Europe and, say, Asia location. But the second update first has to travel from US to Europe, then replicate from Europe to two locations, which is itself and either one of US or Asia, and then act back, right? So this is going to take a lot longer than if you move that Europe tablet leader to US, in which case both those updates, so you've cut one giant leap between US and Europe. So there's a lot of these things that we allow also at a per table level. And in fact, more fine-grained than that, you can create table partitions or a sub-table, right? And you can do it at that level too.
Okay, yeah.
So that was the other part I wanted to cover, but I don't think I could have covered it in the time. So, but
Liz?
I wanted to relate it because you just mentioned that you could keep all the leaders in one location. So what are the downsides of putting all the leaders in one location? I mean, there obviously must be some downsides.
There's a downside, but it may not be much of a downside given the other side, which is that, like, let's say in this example, you have a US, Europe, Asia type deployment, right? 3-continent replication. All your leaders in US, if there's somebody from Asia trying to access data, they need to go all the way to the US to read it, right? You're not going to get it from any of the other locations if you're actually trying to access the true source of truth. We allow follower reads, which is stale copy, but let's ignore that for a second. So if you really want to do any transaction, you have to travel all the way to the US, right? Whereas if you had distributed the data across, you could get some from the other location as well, right? So but assume that you don't have, if you can carefully arrange your data in such a way that you could get your Asia data in Asia and the US data in US, then you can get the best of both worlds, where you can segregate your leaders to have one set of tablets or the leaders that serve Asia data in Asia, US and Europe and Europe, right? So that scheme is called geopartitioning. But the reality is the use cases are mixed. Like, we don't know what, if it is let's take a retail example, right? If it is the products, right? The product catalog, this won't work because everybody needs to view what are the items available, right? But if this is your set of orders, then this will work because that table can now be segmented into the 3 locations and say each user that lives in a certain region can just go to that local region, right? So it's more app development burden or a little bit, but at least there is the possibility of optimizing these things. So there's really no downside to it, except you have to come up with a good location to pick, and that may not be easy. So.
I would say one downside is increased chance of correlated failures when you can, something can happen to this, node that hosts a lot of leaders, so like that region.
Yeah, then we scatter. Yeah, then we scatter. It'll be like, so it'll be a 3-second outage of the entire database as opposed to a subset of the database. Yeah, but that's right. Yeah, but I think practically it's okay. People tend to ignore the subset, the advantage of just a subset being down. So.
Okay. I'm sure this question, like people ask this question a lot, but like you have a very obvious competition out there in the face of CockroachDB, right? So they're trying to do very similar, and it seems like the transaction protocol is also somewhat similar, right? And both rely on HLC. So can you, I guess, can you tell why you're better?
Oh yeah, absolutely. If I cannot answer that, I'm not doing a good job, am I? But anyways, I mean, I'm sure they'll have their point of view. I'll just give like the YugabyteDB point of view. The first thing that we did differently from them is the fact that we reuse Postgres. So YugabyteDB is a Postgres database, which means stored procedures, triggers, any complex Postgres application, whatever it is, will simply run on YugabyteDB. But that's not to say an app built for a single node database is going to run flawlessly on a distributed database with respect to performance, right? So our users, the way they end up leveraging YugabyteDB is they can come from any source database, Oracle, SQL Server, DB2, MySQL, or Postgres, but we ask them to first convert their schema to Postgres and get it to completely work on Postgres, which we have outsourced that portion of the problem because it's a complex problem and we think it's solved well enough in the world that we don't have to innovate on it yet. So people somehow get it to run on Postgres, and once they run it on Postgres, they already know they can run it on Yugabyte because Yugabyte is Postgres, and you now have to just look at your slow queries and start changing your DML, DDL, your actual layout to get efficiency from a distributed or geo-distributed topology. Cockroach speaks the Postgres wire protocol, but is a completely new database. So both these steps are combined in one. So the act of moving out of a database and translating, as well as getting value out of a distributed system, gets combined in one, which makes it very hard for end users to grok or to comprehend, right? Like at least we noticed this with NoSQL systems when we were building it back in Facebook, where the mental load is just too much for people, and they were like, you know what, I'm just better off sticking to my thing and not doing this if it's complicated, right? So that's one. The second big differentiator is the fact that we support async replication in addition to sync, which is an important piece of technology. It's actually complicated supporting async replication on top of a synchronously replicated HLC cluster. But we do that because it is an important piece of the cutting latency in geo-distributed deployments. So I'd say those are the two major ones. I mean, there's a whole bunch of others where we are engineered for performance ground up in C++, and they're like, or didn't seem to have focused on performance from day one, but those are more incidental. Open source, like we're fully permissive license, so everything in the database is completely open, including the enterprise features, right? But Cockroach has a commercial license, so there's other aspects, right? So, but on the core database level, these are I'm talking about the technical level. These are the differences.
All right. Thanks a lot, Karthik. I don't want to hold up you any longer. It's been an hour.
It's been a fun discussion. Thanks, everybody. Really, really fun. Thanks for having me, Alex. This is awesome.
Yeah. I learned a lot. Thanks, Karthik. And I hope we'll stay in touch.
Absolutely. Yeah. And folks, any other questions, feel free to join our Slack. Happy to continue the conversation there. Awesome. Thanks, Alexi. Thank you, everybody. Bye.
Yeah. Thank you. Have a good one, everyone.